All right, so with the last lecture, as I had mentioned, I pretty much wrapped up what I wanted to say about quantum error correction and certain aspects of quantum fault tolerance. So I have included more, a little more hands-on, circuits, working, analyzing fault tolerance in encoding circuits or in gates and so on in the tutorial. So tutorial 3, I believe the TAs want to have it on Friday evening. Does that work for everybody here at least? Okay, first of all, those of you who are here, do you still want a tutorial? Because this tutorial is fairly simple. It's more to give you hands-on experience working with the stabilizer formalism. That's what it is about mainly, stabilizers and a little bit of quantum fault tolerance. So do you guys still want to have a tutorial session? Yes, no? So if you keep quiet, I'll assume that you don't need a tutorial. So in which case, we'll just skip that altogether, right? Yes means what? You want a tutorial. Okay. So at least some of you want a tutorial. So will Friday evening 4:30 work for you this Friday? Okay. So if there's any objection to Friday evening 4:30, let me know. Otherwise, we'll fix up. So there's going to be a colloquium. Actually, there are 2 quantum colloquia this week. So there's one tomorrow, which hopefully all of you have received an email about. There is another colloquium that's going to happen on Friday as well, where in fact someone will be talking about quantum machine learning, which everybody wants to do their project presentation on quantum machine learning, from what I can see. So please attend Friday's colloquium. That'll be 3 to 4. And then we can do the tutorial at 4:30 on Friday. Okay? Right. So that will be the last tutorial on error correction. So the way I see it, we have done so far 3 modules in the course. There was one module just on understanding open quantum systems and decoherence. The second module was basically quantum noise channels and understanding things like fidelity and so on. And finally, we got into the error correction part of it, right? First, we understood how to model errors. We understood the mathematical framework of that. Then we understood how to finally correct them. And then the last step was fault tolerance, right? Okay. So that kind of covers one entire chunk of this course. And we now have the remaining 1/3 of the course roughly, right? And this we will focus on aspects of quantum information theory. So typically people like to divide up this field into computation and information. So let's say algorithms, circuits, all of that fall under computation. So also therefore error correction and things like that. But there is also the whole information theory aspect of it, right? So what is this quantum Shannon theory that I keep talking about? So the way I see it, there are 2 major aspects of this quantum Shannon theory. So one can simply also call it quantum information theory more generally, right? That is what it is. So in some sense, we've already seen certain basic aspects of this in the basic QCQI course, right? Where you look at the nature of quantum information, where you talk about whether states can be distinguished, not distinguished, etc. Where you talk about no cloning, where you talk about entanglement. So these are all certain purity, right? So these are all certain aspects of information processing using quantum states, right? So that is what this area is about. But then there are certain technical aspects of it, which is what we'd like to cover over the next few weeks. So one aspect of this has to do with compressing quantum information. Okay, where you want to basically understand if I need to send a certain kind of information, right? So I'll formulate this question formally for the classical case at least today, right? But the idea is, can you quantify the physical resources, the amount of physical resource you need to transmit quantum information. Right? That is one of the goals of this whole enterprise of trying to compress quantum information. So in some sense, you're asking what is really the information content, for example, of an ensemble of quantum states. So if I tell you that there is a source who is preparing a bunch of quantum states rho I, most generally there will be density matrices, right? Each being picked with some probability pi, right? Then what is the information content of this ensemble? How do you quantify that? Because once you know the information content, then you can answer this question as to what is the kind of physical resource you need to store this information or to transmit this information. But first you need a way to understand what is the information content when you say something like this. Classically, you will say, suppose I have an alphabet which has k letters, right? And I know that each letter occurs with a certain probability. The standard example being the English language, where you have 26 letters. And those of you who play games like Scrabble, or I don't know if you're all doing Wordle and Quordle and all of that these days, then you know that there's a probability game out there. You know that certain these letters occur with certain frequencies or certain probabilities. And then you can ask, what really is the average, if I write an average word in the English language, right? What is the information content of that, right? That is how, for example, I mean, not that you are doing this every time, but your brain involuntarily is doing that when you're playing games like Wordle or Scrabble and things like that, right? Anybody here who plays Wordle? I'm just curious. Do people know of Wordle?
Yes, ma'am.
Okay, so okay, good. So there are people playing this. Nice. I mean, I just don't have the time. Otherwise, I would be playing. I would also be playing this game. All right. So that's exactly what you're doing, right? In some sense, you're asking what is the average information content of an average word or a typical word, and then you're trying to guess that typical word in the least number of trials or whatever, right? Roughly, that's what this is about. So this is a game that you have to play in information storage or communication setting also, right? So the first part will be about understanding the information content, and therefore we will have to understand in that process quantities like entropy, right? So naturally here one has to start talking about entropy and understand its various properties and all of that. So that will become an important, so that is what we'll focus on maybe for a couple of lectures at least. And the next part is to understand information transmission itself, right? So transmitting, and here now there are two aspects to it, because so we all looked at what a quantum channel is, right? That we have already studied in the very first module of this course. And now you can talk about transmitting information through a quantum channel, but what kind of information? Well, you can transmit both classical and quantum information over quantum channels. So I don't know how much of this I will get to cover, but I would like to definitely talk about this notion of capacity, right? I'm putting this out there so that even if I don't get to cover this, at least I give you enough tools to go and understand or read up on your own what this is. So transmitting classical and quantum information over quantum channels, this is one important aspect of quantum information theory or quantum Shannon theory, right? And then this naturally leads to this notion of capacity, right? And there are various capacities that you can associate with a quantum channel. You can, of course, talk about the classical capacity of a quantum channel. You can talk about the quantum capacity of a quantum channel. You can also talk about various other interesting things like entanglement assisted capacity, because now you see we have other fancy things at our disposal, such as sharing entanglement. So there is what is called entanglement assisted capacity, and there is entanglement assisted classical and quantum capacity. and so on and so forth. So there are different kinds of capacities that you can associate with a quantum channel. And I would like to at least talk a little bit about classical and quantum capacity in this course. There is a third aspect which I definitely don't think I will have time to discuss, which is also very much a part of what I would call quantum information theory, and this is the study of quantum entanglement. Because entanglement is an important resource in quantum information processing tasks in general. And we've already seen a basic example of this when we discuss something like teleportation, right? This is something we already discussed in the basic QCQI course. Entanglement was a basic resource for achieving a communication task like teleportation. Now, there are other tasks you can do with entanglement. Another example being some kind of quantum secure communication. So while teleportation itself is not so much about security, but you can use entanglement, for example, to do things like quantum key distribution, quantum secret sharing, etc., right? So entanglement, first of all, understanding these various uses of entanglement, that is an important aspect of quantum information theory. Quantifying, say if I have so much entanglement, what is the kind of secret sharing I can do? What is the kind of key distribution that I can do? How is the security of that protocol related to the entanglement and so on? And then there is the whole aspect of quantifying entanglement itself. If I give you a certain state, certain bipartite or multipartite quantum state, how much entanglement is there in the state, right? So basically one can say that this whole area is about quantifying and using entanglement, right? So it's both about quantifying and using entanglement. As a resource for quantum information processing. So this, I don't think I will have time to get to in this course. When I imagined this course, this was also something that I would have ideally liked to talk about, but I don't know how much time, and certainly I don't want to do an information overload. We all want to be within our capacities, so I don't want to stretch our information capacity also. Ultimately, capacity is also about achieving a certain fidelity in information transmission, right? So we don't want to lose out on that by putting too much information. But yeah, this is also, I just want to point out, this is also something that people is very much an interesting area to study, and it's something that people have studied and people are continuing to study, okay? Right, so like I said, we'll focus on the first two aspects by and large, and if we have time, we'll maybe see a few glimpses of certain aspects of entanglement. So this first two aspects, which is about information, content, compression, and capacities, transmission of information. So this is basically what you'll find in chapters 11 and 12 of Nielsen and Chuang. So for error correction, I think I had referred you to chapter 7 of Preskill notes. Now, this is chapter 10 of Preskill notes, okay? There is also a whole book on quantum information theory, for those of you who really are interested in the subject, by Mark Wilder. And I think this book is a Cambridge University Press book, but it's available fully on the archive. So if you just go on archive and look for this book, you will find the entire book. There's a more advanced, or shall I say more mathematical book. So this is one, and there's another book by John Watrous. There are also lecture notes online by John Watrous. So these are all nice resources, slightly more advanced resources for quantum information theory, right? So I hope I get to do some justice to the subject over the next few weeks. It's a very interesting area. And let's see how far we get. Okay, fine. So with that broad introduction, let's get started. So the first thing to study, like I said, is to understand information content, right? And obviously the first quantity to understand is entropy, right? So, and I think for us, it is important to understand both classical and quantum entropic functions. So what I mean by a classical function is the Shannon entropy, right? And what I mean by a quantum entropy is the so-called von Neumann entropy, right? And it will be important to understand both of these. So you can associate with a given quantum state, rho, you can associate both a classical Shannon entropy and you can also associate a quantum entropy, which is the von Neumann entropy, right? So it's important, in my opinion, to understand the properties and both these functions, right? Both entropy functions. The quantum one, of course, being inspired by the classical one, which of course came first, historically also. Actually, I'm not really sure about that because I think von Neumann already looked at something like this entropy function. Anyway, we physicists like to believe that we have been looking at entropies long before people in information theory and communication started looking at it, because we have been worried about entropy from a statistical mechanical perspective, right? And those of you who have done StatMech courses would have seen your Boltzmann definition of entropy and all that, right? The Shannon definition is not that different, right? Although, yeah, I mean, there's a big debate about how you can relate one to the other and so on and so forth. But my opinion, the underlying idea between something like the Boltzmann entropy of statistical physics and the Shannon entropy is not too different, right? It's the same. Okay, so now I want to ask, how many of you here, or are there people here who have done a course on classical information theory? Because I know there's a lot of MSc students who probably haven't done such a course. So I usually, or the last time I did this course, at least I spent some time discussing just the classical Shannon entropy. So shall I do that, or will that be too redundant for most of you? Should I skip it? That's what I wanted to take a quick poll from those of you who are here at least. So shall we spend some, yeah?
We can have a quick review of classical because MSc students have not done such a course.
All right, okay, cool, thanks. So let me do that then. Okay, so let's start by discussing Shannon entropy. Of course, the idea goes back to Claude Shannon, this very seminal 1948 paper. Forget the title now, I should remember this, but anyway, I'm sure you Google and find this paper. So let's try to understand, so what do I mean by trying to understand entropy? So we have to try to understand what is the motivation for defining a function like this, and what does it signify purely from an information theory perspective, right? Because that's what we are interested in understanding. So it all begins with having a random variable, let's call the random variable x, right? And let's say that x takes on values x1, x2, etc., xn, right? So this is where the story begins. Now, what is this? So for example, this could be the outcome of a coin toss, which then takes on values head or tail, right? It could be a binary alphabet, which takes on 0 or 1, right? It could be a general K letter alphabet. So each xi can be either 0, 1, 2, 3, etc., K minus 1. And all of this occurs with some probabilities, right? Of course, roll of a die, etc. So with probabilities, so I'm talking about it as a discrete set now. So I have a random variable which can take one of these little n values, and these little n values occur with these probabilities p1 to pn, such that sum over I pi is 1, of course, from 1 to n, right? Now, the question that Shannon was trying to ask from an information theory perspective is how much information is gained when we learn the value of x. Another way of phrasing it is how much uncertainty is there in the value of x, right? How uncertain is the value of x, right? And this is what Shannon proposed, that we quantify by a function which is called h of x, which is simply, so you can also think of it as h of this probability distribution p1 to pn, right? So I will also write it like this, which is simply negative sum over I going from 1 to n pi, so often defined log with respect to base 2 pi, right? So this is the basic definition of the Shannon entropy for a random variable x, which takes on one of x values with probabilities p1 to pn. Then the Shannon entropy associated with this random variable is this, right? So this is a mathematical function that is defined. Now, why does it have this meaning, right? Or does it have this meaning, right? Why is it that the amount of information gained when we learn the value of x, or how uncertain are we about this random variable x? Why is that quantified by this negative of pi log pi, right? What is the motivation for this? So just quickly, because it's an interesting question to ask, why should this be the definition of, why should this have this interpretation? Why should this function have this interpretation? So what Shannon posited in his paper is that he said that what we are after is what is called the information content of this random variable, or this, you can more loosely say, of this probability distribution. In particular, you can talk about, so now this random variable, meaning each time that you sample, you're going to get some value, right? So each of this is what in probability theory language you will say is an event. So what is the information content of an event E? Okay. Which occurs in some probabilistic experiment. So Shannon proposed that a function which quantifies this, right, or a mathematical way to quantify this information content must have certain reasonable properties, right, or must satisfy some reasonable axioms. Okay. And what are these reasonable axioms that he said? So you understand, each time I pick a letter, let's say if it's an alphabet and I'm picking a letter, that is one event, right? Each time I'm sampling this distribution, and each realization, so let's say of this random variable, is one event, right? And each time such an event occurs, how much information are you gaining, right? Or how much uncertainty did you have before the event occurred? That's what you're trying to quantify. And in doing so, Shannon said that this kind of a quantity must satisfy some reasonable axioms. First of all, this information content function, he called it I think, and this should be a function of the probability of the event, and it should be a smooth function. So he said this is a reasonable thing to demand, that it must be a smooth function in the very, when one can make this more precise in the in the analysis language, right? But I won't get into that. And the second basic assumption has to do with, so of course you can put some limits on this and say that this has to lie between some 0 and some number, right? Whatever, that could be 1 or something. But basically, if you are, I mean, if it is, if it's an event which is occurring with probability 1, then there is no information content every time it is realized, right? That's like, in the quantum mechanical sense, the way I would think of such an event is I measure, and I'm already sitting in an eigenstate of an observable, or I prepare, let's say, the 0 state, the ket 0, and I measure sigma z. What is the uncertainty in the outcome? Nothing. I know exactly what I'm going to get because I am in an eigenstate of this observable. What is the information content of this realization of this event? Nothing, right? So that's when you say that this information content is 0, and then you put some maximum to it. It need not be 1, but let's say that must be a positive quantity, right? And we don't have to put an upper bound, that we can normalize and so on. But the other main important thing, property he said, has to do with independent events. And this is where really the log function comes in, right? Because he said that the information gained when two independent events occur, let's say with probabilities P and Q, right? So, for example, two successive tosses of a coin, right? Generally assumed to be, it's reasonable to say that they are independent, right? Unless you believe, like certain people do, that Virat Kohli always goes and loses the toss. Normally, these are assumed to be independent events. Whether Virat Kohli wins the toss in the first test match is completely uncorrelated with whether he will win the toss in the second test match, right? So when two such independent events occur with probabilities P and Q, what should be the information gained? It should be the sum of the information gained from each event. Right? So in other words, he said that there should be some kind of additivity property, right? This is what you would call an additivity property for independent events, right? Because these two events are independent, each time this happens, I'm gaining some additional information, right? Because these outcomes are not correlated with each other, each time I realize this, I'm gaining additional information. And so this should be an additive quantity for independent events. And naturally, you see that I of p equal to minus log p is a function that satisfies all these properties. Right? P is something that is between 0 and 1, so negative log p will be positive, and this is a smooth function, and for independent events, you will naturally satisfy this property, because you know that the probability of independent events is the product of the probabilities, right? So the information content should add up, right? There is additional information gained with every successive realization of an independent event, right? So what the Shannon entropy then is, it is simply the average information gain for a random variable x, right? And the average information gain, so for each outcome or for each realization, the information gain is a negative log of that, right? So the average information gain would be sum over I pi, right, if I have I possible outcomes for this random variable, times the information gain each time, right, which is I of pi. And so this gives you minus pi log pi. So the way that people in the classical information theory literature will often define Shannon entropy is as the average of the negative log function, right, or the expectation value of negative log pi. So these are all equivalent ways of talking about the Shannon entropy, right? So, few things to note about this. So one important kind of Shannon entropy that is often spoken about is what is called the binary entropy, because we are, of course, interested in binary alphabets all the time, and we are interested in qubits as far as quantum information is concerned. So this is basically a two outcome random variable, right? So this, then you have, let's say, 0 and 1, for example, and these occur with probabilities p and 1 minus p. So the entropy of this two outcome random variable is often denoted with a different symbol with small h. So this is simply called small h of p, the binary entropy, and this is nothing but minus p log p minus 1 minus p log 1 minus p, right? And you can actually plot this function as a function of p, and you notice that, so where does it peak? So of course note that in the limit as p tends to 0, what is this function?
0.
It's 0, and in the limit of 1 also it becomes 0. So you note that, so please recall from whatever, if you have done an analysis or you've done StatMech also, you will see things like this. So what is limit as x tends to 0 x log x?
0.
Yes, so please keep this in mind. So then you notice that this is the shape of this function. I'm sorry, I meant to make it symmetric, about half. And what is the maximum value that h of p can take? Yes, what's the maximum value when p is half?
Log 2.
Which is, since we are all in base 2, that
Oh,
is
1.
1. Okay, remember that we'll be working with log to the base 2. Okay, so for this binary case, indeed this satisfies 0 to 1, right? The binary entropy lies between 0 and 1, and h of p is equal to h of 1 minus p, and it attains its maximum value at p is equal to half. And you notice from the very shape of this function that this is a concave function. So we'll come back to this. We'll come back to the concavity property. Again, that's an important property of the Shannon entropy to observe. And more generally, you notice that if I have this random variable with n outcomes, right? We said that this is minus pi log pi. So what are the limits of this? So you see that 0 less than h of x less than what? So first of all, when is this entropy 0? For a more general probability distribution, not a binary variable, but a general variable, this is 0 when, what is the distribution for which this is 0?
Delta, like a delta function.
Yeah, so when pi, so this is what is called, so this distribution is a, what's called a point mass or a delta distribution, right? Which means that pi is 1 for a particular I, and 0 otherwise, right? So this is the case where you're absolutely certain of the outcome of this probabilistic experiment, and there is no information gained in sampling or in realizing a particular outcome, right? And of course, like I said, the canonical example would be to measure an eigenstate of an observable, right? And you know exactly what outcome you're going to get. It is a delta distribution, right? What is the maximum value of this? There are n possible outcomes. So what is the maximum value?
1 by n.
Mm,
Essentially log to log n.
yeah. So the maximum value has to be log n. And why is that? So when does it attain its maximum value? It attains its maximum value when
It's a uniform distribution.
yeah, indeed. So when pi is a uniform distribution. Right? So right now, I'm not really proving this. I'm more arguing this from an intuitive kind of perspective, right? Where I'm saying that I have these n different possibilities. On one extreme is a point mass distribution or a delta distribution, where only one of these events actually can occur with non-zero probability and everything else has zero probability. And on the other extreme is a case where all outcomes are equally likely. And that is when you learn most from each realization of the experiment. That is when you are most uncertain about the outcome of this experiment, right? So it attains its maximum value when all outcomes are equally likely. And so each pi is then 1 over n for all I, right? And so h of x is then minus sum over I going from 1 to n, 1 over n log 1 over n, right? And so you're doing this n times, and negative log 1 over n simply becomes log n to the base 2, right? So this is the maximum value that the Shannon entropy can take when you have n possible outcomes. You have a random variable with n possible outcomes, right? So again, let's look at a quantum measurement scenario where you see this maximum uncertainty come into play. So suppose you measure sigma z, the z observable, on the plus state, right? So you know that plus is 0 plus 1 over root 2. And so you know that probability of outcome 0 is the same as probability of outcome 1, which is a half, right? So each time you measure, you make several copies of the plus state, and each time you measure sigma z, you're uncertain about whether you're going to get 0 or 1. You're maximally, in some sense, uncertain, because if I had any other coefficients there, there's a certain bias to either 0 or 1, right? But now you're truly maximally uncertain about this outcome, and the Shannon entropy that you can associate. So you realize that every time you measure, right? So every time you measure a state, some observable on a state, you have a certain probability distribution, right? There is an outcome distribution. And so naturally, there is a way to associate a Shannon entropy with the measurement outcome, right? And so, in fact, in the quantum mechanical setting, the Shannon entropy becomes a natural way to actually talk about uncertainty in the measurement outcome. So I must have given you a problem about the uncertainty principle when we did the basic QCQI course, or if you've done any quantum mechanics course or so on, you have seen problems about, you've seen the uncertainty principle. And normally one talks about uncertainty in terms of the standard deviation associated with the probability distribution over the set of outcomes, right? But now I just want to mention that you can in fact talk about an entropic uncertainty principle. And I just want to mention this briefly. I'll see if I can throw this into the problem set, but you can go ahead and read this up in Nielsen Chuang. This is box 11.1, where they talk about this entropic uncertainty principle. This, I think, is a very nice example of how ideas from classical information feed into even our understanding of basic foundations of quantum mechanics or foundations of quantum theory, right? Because we're used to talking about uncertainty in terms of standard deviation, right? But you realize, so let's say the standard uncertainty principle. So let me just spend a few minutes on this since I'm here. So the standard uncertainty principle says that if I have two observables A and B, then the product of the standard deviation, when you measure these observables in some state psi, this must be greater than or equal to the expectation value of the commutator of these two observables, right? And then there is a 2 or root 2 or something like that, right? So this is the standard uncertainty principle, right? But now it can happen, for example, that there are observables where this right-hand side can vanish simply because, not because the commutator vanished, right? But because there are states on which this commutator doesn't have support, right? So this need not be a full capture of uncertainty as such. And it was proposed by people like Deutsch and so on, the same Deutsch of the Deutsch algorithm in the 80s, that maybe it is useful to actually quantify uncertainty not using the spread of the distribution, but using the entropy. And now, mind you, one is talking about classical entropy functions like the Shannon entropy. Deutsch had a different kind of entropy function in mind when he proposed this, but you can equally well talk about the standard Shannon entropy, right? So let's say that I have observable A, and let's say that A has all these eigenvalues, right? Eigenstates, get A1, get A2, etc., get AN. Or get AD, let me say, we are in a D-dimensional Hilbert space. And let's say I have another observable B. So these are the eigenstates of A. And you know that the eigenstates of an observable form an orthonormal basis, right? So this is one orthonormal basis actually for this Hilbert space. And then I have another observable B with eigenstates B1, B2, etc., B sub D, right? Then you can measure state psi. So you measure observable A on set of independent, let me say that you make several, okay. So let's say that you want to talk about the uncertainty in the measurement of A and B on some state psi, right? So first of all, you note that this uncertainty principle, it heavily depends on the state psi, right? This is, and what is on the right hand side, whatever quantity you get is something that depends on the state psi, right? Although with something like position and momentum, you have a state dependent lower bound, but this actual quantity itself many times can depend on the state psi. And if you want to minimize over psi, then there's a problem that you may end up with a zero value out there, right? But the entropy function might therefore be a better way to do this. So let me just write down an entropic formulation of this uncertainty principle. So what do I mean to say uncertainty in measurement of these two observables on some state psi? It means that I consider many independently prepared copies of state psi, okay? And then I independently measure A on some of them, and I measure B on another set of them, on another subset of them, right? And then this gives me a probability distribution over the outcomes, right? Because the outcomes, we have labeled the eigenstates using the outcomes, right? So the outcome, the probability, let's say, of outcome I, when you talk about observable A, is going to be the overlap between the corresponding eigenstate and the state on which you measure modulus squared, right? Similarly, so let me say this is probability of outcome I when you measure A in state psi, okay? And let's say that this gives rise to a different probability distribution, which I call QB. Again, I put the state psi here for reference. Probability of outcome J is this overlap function, modulus squared, right? So this, of course, I going from 1 to D. This is J going from 1 to D. I'm not saying anything new here. This is something we discussed in measurement theory last year, right? That the probability of getting outcome, a particular outcome, is related to the overlap of the corresponding eigenstate with the state on which you're doing the measurement, right? This is the, so now you have these two probability distributions, right, associated with these two outcomes, and it turns out that you can actually formulate an uncertainty relation using these two distributions. I'll simply call it PAI. So this is the Shannon entropy of this distribution. So you can actually take the sum of the Shannon entropies of these two distributions. So then you can do H of, so I should put a curly brace here to say that this is the Shannon entropy of this distribution, this probability distribution, I going from 1 to D. You have another probability distribution QB of J, right? Again, J going from 1 to D. So that's why I put this curly braces here. The sum of these two Shannon entropies, it turns out, has a non-trivial lower bound, right? And this lower bound on the sum of these two Shannon entropies, it was shown sometime in the 80s that this is actually bounded, this can be lower bounded by a quantity which only depends on A and B, okay, which is completely independent of the state, right? And this then constitutes what is called an entropic uncertainty bound. And this is a very useful sort of measure in quantum information theory, because I want to know, for example, if I want to send information across, right, and if I want to use two different measurement bases, so if I want to use two different orthonormal bases to send information or to store information, right, which are the bases which are most uncertain with respect to each other, right? And this sum of Shannon entropies and a lower bound on that will tell you how uncertain you are about A with respect to B. So for example, if I am in an eigenstate of observable A, then how uncertain am I about B? If I'm in an eigenstate of observable B, how uncertain am I about A? So why does the sum have a lower bound? Because, I mean, just like how you had a trade-off in the standard deviation here, right, earlier, now you can argue that if I'm in an eigenstate of A, then this entropy will vanish. But if these two observables are maximally uncertain, like the sigma x and the sigma z, then this entropy can actually be maximum, right? So let me say that in the example of sigma x and sigma z, if this vanishes, then this is maximum. And what is that maximum? That is essentially log B, right? If it is sigma x and sigma z, then it is log 2, which is 1, right? So, and then you can say vice versa. So when this happens, so when you have two observables with this property, that if one of them, you are completely certain, right? And you're completely certain only because you will be in an eigenstate of that observable. Then you're maximally uncertain about the other observable, which means you attain this maximum entropy. That's when you say that these two observables are maximally complementary, right? Or they are you have this maximum uncertainty between the two of them, right? They are maximally incompatible, for example. So this is the maximum uncertainty that you can have about one observable versus the other. So you can also say maximum incompatibility. So this kind of a technique is also sometimes used to prove that certain quantum communication protocols are secure. For example, security of what is called quantum key distribution can be proven using something like an entropic lower bound like this, right? So maximum incompatibility or maximum uncertainty means that if you're an eigenstate of one, which means that one entropy vanishes, the other entropy becomes maximum and vice versa. Okay, so this is just to tell you how the Shannon entropy actually plays an important role in various aspects of quantum theory, even foundational aspects or fundamental aspects like talking about incompatible observables, all the way to being a parameter in a security proof of a communication protocol. Okay, any questions? Okay, so I encourage you to go and read box 11.1, which will say more about this entropic uncertainty principle, and I also maybe throw in a tutorial problem set for the next tutorial. So let's go back to our discussion of the Shannon entropy. We saw that the binary entropy is concave just by plotting it, and then we saw the lower and upper bounds on this. Then I kind of segued into this measurement aspect. So let's get back to discussing some more useful properties of the Shannon entropy. Yeah, so the next thing to ask, so there are a few things that, so let me just list what I call properties. And let's say that our reference will always be X, which takes on one of n possible values, right? So the first thing was that it lies between 0 and log n to the base 2. The second thing which I want to look at is the concavity of the entropy. Which means what happens when I have, how is the entropy of a mixture related to the entropy of the individual distributions? So let us consider a mixture of probability distributions. What do I mean by a mixture? So that's a convex sum, right? And as you can see, this question will naturally occur in quantum information theory because we're all the time taking convex linear combinations of density operators and states and so on, right? And you want to understand how the entropy behaves when you take a convex sum, right? So let's say, for example, that you're back to the binary entropy. Let's say that you have two binary random variables. So let's say P1, 1 minus P1, and Q1, 1 minus Q1. I can just say P and Q, but we say that it's P2 and 1 minus P2. Okay. And now I form, okay, this is why I didn't want to use P here. Now I form a mixture, right? So I consider another distribution, which is alpha P1 plus 1 minus alpha P2, right? So if Q is this, then what is 1 minus Q? You can jolly well work out that 1 minus Q is alpha 1 minus P1 plus 1 minus alpha 1 minus P2. So this is a new probability distribution. It's another binary probability distribution, which is realized as a mixture of these two distributions, the first two, the P1 and the P2 distributions, right? So now the question is, what is little h of Q and how is it related to little h of P1 and little h of P2. So this is alpha P1 plus 1 minus alpha P2. That's what Q is, right? So one can show that this is greater than or equal to alpha h of P1 plus 1 minus alpha h of P2. Okay. So this is what you mean by concavity. Or a concave function. Okay. So I'm not going to prove this. I will rather prove the concavity of the von Neumann entropy going forward. Okay, but I will just note this. But how will you prove this? Or why is this concave? What underlies the concavity of the Shannon entropy? Mathematically, what function is it? It's a log function, right? So the proof will essentially follow from the concavity of the log function. That's all, right? It's essentially negative pi log pi. So since log is a concave function, obviously this also becomes a concave function. What that means is when you take a convex sum like this, right? So of course I should mention when I say alpha 1 minus alpha, I hope it's obvious that alpha is something that is between 0 and 1, right? So this is what you would call a convex sum of two probability distributions. And when you do that, the resulting entropy is always greater. So what the concavity property tells you is that the entropy of a mixture is always greater than or equal to the sum of the entropies or the convex sum of the individual entropies. And intuitively, this also makes sense, right? I have a certain amount of uncertainty about the random variable individually. Let's say that this was x1 and x2, two different random variables. Now I'm making a third random variable, which is now a convex sum of the first two. So obviously this mixture I will be more uncertain about than the convex sum of the individual, right? Okay, so maybe the last property that I want to talk about is a sort of physical meaning for the Shannon entropy from a information storage or compression point of view, right? So let us talk about, okay, maybe before that, I want to talk about subadditivity. Okay, so maybe let me talk about those things first, and then next time we will talk about compression and typicality and all of that. So let me complete this discussion of properties. So the third property is what is called the subadditivity. And this is a very important property. We will also look at this in the context of the von Neumann entropy of density operators also. So the subadditivity of the Shannon entropy. So this says that when I have, so before that, let's say that I have two random variables, x and y, right? And I can talk about the joint entropy, and this is often denoted as h of x comma y. What does that mean? So I will say associated with x, I will call this, so I will slightly change notation now, and I will call this T of x as the probability distribution that is associated with x. So if you want, you can put a P of xi here if you wish. So that I goes from 1 to something. But more generally, I'll simply talk about it as P of x. Okay. And y is distributed according to some P of y. You can even make it Q of y just to separate out the thing. Then you obviously have a joint probability distribution, which is P of x comma y, right? So let me call this also P only to be consistent, right? Now P of x comma y may or may not separate out into the product of the individual probabilities. When does it separate out to be the product of the individual probabilities? Yes?
Independent.
Yeah, only when they are independent. So P of x comma y for independent random variables P of x comma y is nothing but P of x times P of y. Otherwise, it is simply the probability of random variable x taking the value x and the random variable y taking the value y, right? It's a joint distribution. So you can therefore talk about a joint entropy, which is simply sum over all x and y, P of x comma y log P of x comma y, right? That's what the joint entropy will be defined as. And you can add as many random variables as you want, and you can define joint entropies for all of them, right? What subadditivity of the Shannon entropy tells us is that this joint entropy always satisfies h of x comma y is less than or equal to h of x plus h of y. With equality if and only if. So what does equality mean? It means that the joint entropy is simply the sum of the individual entropies, right? And when will that happen? That's the case we just discussed, when the probability distribution factors out into a product distribution, right? Otherwise, what is it saying? It's saying that if I have a joint distribution over two random variables, x and y, and I learn something about x and y, then if there is any correlation between these two random variables, I'm actually learning something less than what I would have learned individually if I had, realized x, and individually if I had realized y. So in a joint realization of x and y, I'm learning something less than an individual realization of x and individual realization of y. Or if my random variables are correlated, they are not independent, then the uncertainty in a joint value of x and y is less than the individual uncertainties in the individual random variables, right? And these two are the same if and only if x and y are independent random variables. Because in that case, h of x comma y is simply h of x plus h of y, right? So this is a useful property to learn, also how to prove this property. And it turns out that in a simple way to prove this property is to use something called the relative entropy function. So that's what I want to define here. So I'm kind of rushing through this because we're going to go over all of this again when we do quantum entropies. So this is more of a, because classical entropies, maybe it's easier to deal with a little bit, because these are, you can just think of them as log functions and, understand using the property of the logarithm, right? So let us understand. So the proof of this, in order to understand this, so this is the third property I think I was writing down. So I will just say 3a. I will talk about the classical relative entropy. Again, one is going to very soon define a quantum relative entropy, so it's useful to know the classical entropy as well. So the relative entropy is a way to quantify how close two probability distributions are. So let us say again P of X and P of Y, right? Oh, it's Q of X. No, it doesn't matter. How close are two probability distributions? So P and Q are two probability distributions over the same random variable X, let us say, for example. How does one quantify the distance between two probability distributions? So remember, we spoke about distance between quantum states. We spoke about fidelity. I told you that the fidelity itself is related to a classical probability distance measure called the Bhattacharya distance between two probability distributions. And that distance measure was based on the sum of the square root of the products of these two probability functions. But this is now a very different way of talking about the closeness of two probability distributions. In fact, we have an exact analog in the quantum information context called the quantum relative entropy, and we'll define that very soon. So by now, it should be clear to you that the analog between the probability distribution function, which one talks about in classical information, what is the quantum analog for that? The density operator. So when one talks about distance between probability distributions, in the quantum setting, that translates to distance between two density operators. So the fidelity is one such distance, which is in a certain limit, it will lead you to the classical distance between two probability distributions. Similarly, the relative entropy is another such measure of distance. So let me define it first. So it is defined with this symbol, double line, between the two P of X and Q of X, and it's called H of P of X, Q of X. This is the relative entropy. This is defined to be, so this is just the definition, sum over all X, P of X, log of P of X by Q of X, right? Or another way of writing this is sum over X, P of X, log P of X minus sum over X, P of X, log Q of X, right? Another way of thinking about it is it's minus sum over X, P of X, log Q of X, minus the Shannon entropy of P of X, sorry. So these are all equivalent ways of thinking about it, but this is the basic definition, right? It is nothing but the Shannon entropy of this distribution P of X minus, what is this? In some sense, this is the expectation value of log of Q of X, where each term is now picked with the probability P of X and not Q of X. So it is an expectation of log Q of X with respect to P of X. Okay, so in some sense, you're comparing these two expectation values of P of X versus Q of X, both sampled according to the same distribution P of X, right? Okay, so why is this distance? Why is this a distance measure, right? So what happens if, so let us note some limiting cases, or actually let us just prove one limiting property of this. So I'll just prove one property of this and then stop, and then we'll continue on Monday. So by the way, on Monday, I will most likely do an in-person lecture. I will update you by tomorrow evening where the location will be and so on. Those of you who are attending now, how many of you can attend an in-person lecture on Monday, or how many of you cannot? Let me ask you this first. How many of you here cannot attend an in-person lecture on Monday? I see one hand raised. Neelkant, you're not yet back on campus?
I mean, I'll be back on campus by 2, but then there is 3 days quarantine.
Quarantine, okay. Is that the situation with many of the MSc students in the class?
Ma'am, I am under the same situation as Neelkant as well. That I
Okay,
will be back at 2 and will be then 3 days quarantine.
I see. So will it be better if I start in person the following week, which is 11th April, right?
Yes, ma'am.
Okay, so from 11th, there'll be more of you who can attend, right? So let me do that then. Let me start in person from 11th because I don't see the point of doing an in-person lecture if there's only going to be 5 of you in class and everybody else is online, okay? So, okay, so then I will start from the next week so that we'll have at least 2-3 weeks where we can do in-person lectures, okay? All right, so let me conclude with this one theorem that I want to prove about the relative entropy, and that is the positivity of relative entropy, or the non-negativity of the relative entropy. By the way, the relative entropy, just for those of you who know some classical probability and all that, is the same as what is called the Kullback-Leibler divergence. Okay, and what is this positivity statement? It says that this relative entropy quantity between two probability distributions P of x and Q of x is always positive, okay, with equality if and only if P of x is equal to Q of x for all x, for all values x of the random variable capital X can take, okay. So this is what makes it a valid distance measure between probability distributions, because it vanishes if and only if the two distributions are equal, and in every other case it is some other positive quantity which tells you how close or far apart two probability distributions are. And it turns out that the positivity simply follows again from just properties of the log function. So it's all playing around with the log function, right? So just note, so what we will use in the proof is simply this, that log x times ln 2 is the same as, so what is ln? Ln is a natural log, not log to the base 2, but natural log. So just note this relation between, and the natural log, you know, is always less than or equal to x minus 1. So this is something that I leave for you to prove or check, right, for all x, positive x. And also note that this is satisfied with equality if and only if x is equal to 1, right? So for the natural log, I mean, you can just even do a graphical proof of this. You plot your log function and you plot x minus 1, and you will see that the log function will always lie below the line x minus 1, and the equality happens only at the point x is equal to 1. They coincide at x is equal to 1. And this natural log is related to the binary log via the natural log of 2, right? That's all you need to know to prove this. So it's just a two-step proof. So let me just write that down and then we'll stop here. So you want to look at this relative entropy. This is defined now as minus, so I defined it as plus px log px by qs. I'm going to put a minus sign, so it becomes log qx by p of x. Then obviously I'm going to convert it to a natural log and then use this property, right? So I'm going to say that this is the same as minus sum over x p of x, natural log of q of x by p of x, times or rather divided by log 2, right? So I have to put a 1 over natural log of 2, right? So then this natural log function is always greater than or equal to q of x by p of x, right? So this is greater than or equal to minus 1 over log 2 sum over x p of x natural log of oops, just, so it's q of x by p of x minus 1. So I will get rid of the minus sign. So that will become 1 minus q of x by p of x, right? Oops. And then you can see that this, the first term is just 1. The second term is also 1 because the p of x gets cancelled out. And so this whole thing is simply 0, right? And this is the only inequality step. And this step is saturated with equality if and only if this x is, so there I said natural log x is always smaller than x minus 1 with equality only if x is equal to 1. So x is equal to 1 in this case will mean that q of x by p of x is equal to 1, which means that q of x is equal to p of x. So that's it. We've shown that, and this is a very nice and simple proof. When you come to the quantum relative entropy, you will see that you'll have to sort of huff and puff a bit more to actually even prove this simple property of non-negativity or positivity of the quantum relative entropy. Okay, classical is a very nice function. The log is just taking off from properties like this of the log function, right? So in fact, I said earlier that we didn't prove that the maximum value of the Shannon entropy is log n or log d when you have a d outcome random variable. It turns out that that can actually be proved as a simple corollary of this. So, and I'll leave it to you to do this as homework. So the corollary I want you to show is that the Shannon entropy of a random variable x with, let's say, n outcomes is always less than or equal to log n. And the way to show this from relative entropy, the hint is to consider the relative entropy of any distribution like this distribution. You can, if I call this distribution as p of x, right? Consider the relative entropy of this distribution with respect to the uniform distribution. And then use the positivity of relative entropy. That's all. You're done. You see, this then will give you a relation between the entropy of any distribution and the entropy of the uniform distribution. And you will see that the entropy of the uniform distribution forms an upper bound for the entropy of any other probability distribution. That's what this relation is telling you, right? So just by considering the relative entropy between these two distributions and using the fact that this relative entropy is always positive, you can prove this fact. Okay, so I will stop here and we'll continue tomorrow, where I want to use again the same thing, the positivity of relative entropy, to not tomorrow, I'm sorry, on Monday, where I'll use the positivity of relative entropy to talk about subadditivity. And then we'll talk a little bit about information compression, Shannon's noiseless coding theorem or source coding theorem. And then we'll jump into quantum entropy, von Neumann entropy. Okay. Any questions?
Excuse me, ma'am.
Yeah.
So, like, we were looking at the entropies of this information. So, I wanted to ask that, means even in this case, would the second law of thermodynamics hold that the entropy always increases?
Under what? Entropy always increases under what? When you say second law, you should now say it formally or clearly, right? So for example, I already showed you so we looked at this property, right? Entropy of a mixture is always greater than or equal to the convex sum of the individual entropies. So mixing could be one process, right? And what this is telling you is that the entropy always increases under mixing. So yes, actually the answer to your question, the short answer is yes, but now you have to carefully apply the statement of the second law. right? So okay, let's go back to thermodynamics. So can you tell me what exactly the second law says about increasing of entropy? Under what kind of processes?
So like under irreducible processes, the
Ah,
entropy of the system increases.
Exactly. That's the point. Exactly the same, right? So when I do a mixture like this, that is an irreversible process. On the other hand, if I did unitary dynamics, so you will see this in fact when you come to the von Neumann entropy next week. You talk about the von Neumann entropy of a quantum state or a quantum density operator. Then you can ask, under dynamics, how does this entropy change? And then you can show both things, that if something is a reversible process, then it's a unitary, you can always model it as a unitary dynamics. So under unitary evolution, the Shannon entropy will remain invariant. The von Neumann entropy will remain invariant. So also the Shannon entropy associated with the density operator. I have not yet defined for you what that Shannon entropy is, okay, for a density operator. But once I define that, indeed, you will see that for unitary dynamics, the entropy will remain the same. And what are the irreversible processes? That's what we've been studying all along, right? Mathematically, how do you model irreversible processes? Pratik, right?
Yes, ma'am. Actually, I can't recall. Sorry about that.
No, what we have been studying, no, what is noise?
Oh, okay. Yeah, yes, ma'am. Noise channels.
CPTP
So,
maps, right? Completely positive trace
yeah.
preserving maps, open quantum dynamics, open system dynamics. That is what is irreversible, right? So under CPTP maps, under quantum channels, you can show that the entropy will always increase. Okay? So yes, you very much have a second law like statement, provided you pin down what you mean by reversible and irreversible processes. That's all. Okay?
Yes, ma'am. And ma'am, then related to this previous question,
Hmm.
I mean, like if the, I mean, since the information is directly related to the entropy, so like the increment in the entropy corresponds to the increment in the information, right?
Correct.
So, I mean that the information doesn't remain conserved, right?
Under these kind of processes, you're saying. Yeah.
So like well, like in such cases,
That's the
like in
point,
this,
right? So yeah, exactly. Okay, so let me understand, if I understand the question correctly. Now, when I discuss these kind of open quantum systems, and I said there is an irreversibility about these processes, they are not unitary processes. There is associated with these processes a certain information leak. That information leak is what manifests as this increased entropy. And that is why you lose information, right? So when I mean, in a very simplistic way, if I talk about encoding information and so on, what happens to these states when they are affected by noise? They change. So for example, something like a pure state, and we've seen this often, what happens to a pure state under a open system evolution? It becomes a mixed state.
yeah, it's
That
mixed.
is exactly like going from a zero entropy situation to a non-zero entropy situation. And that is exactly associated with a certain amount of information loss, which is why we studied this whole idea of error correction and information. So in a sense, what error correction is trying to do is some partial information retrieval in the entropic sense. In fact, if you're interested, there are papers which look at quantum error correction itself from an information or an entropy point of view, where you can show if if your noise affects your system in a certain way and you lose information in a certain way, which you can quantify based on the entropy of the output state after the action of the noise, you can ask, after error correction, how much information are you able to retrieve, again from purely an entropic point of view. So there's a way to understand error correction in terms of this whole information or entropic angle, right? So yes, very much so. There is a loss of information that accompanies this. So when entropy increases, your uncertainty increases. You understand, which means that you are now less certain about something. So you have lost some information. In fact, this is also the problem of quantum communication, that when your states pass through a noisy quantum channel, they get corrupted, and therefore there is an information loss. And so how much information can you really communicate over a noisy quantum channel? So that leads to notions of capacity and all of that, right?
Yes, ma'am. Got it. Thank you.
Sure. Any further questions? If not, I will see you all on Monday. So there's some questions on the chat, is it? But anyway, I don't see Siddharth here. Maybe I already answered his questions. Okay, see you all on Monday. I will start in-person lectures on 11th so that the MSc guys can also attend, whoever is here.